So let me welcome CJ. Welcome, CJ. CJ is going to talk about HPC and AI. So let me introduce CJ, our speaker. So it's Chris J. Newburn that goes by CJ. It's a principal architect in the compute software group at Nvidia, where he leads HPC strategy and the software product roadmap, with a special focus on systems and programming models for scale. CJ is the architect of Magnum IO and the co-architect of GPUDirect Storage. Heads the Summit Dev2Dev Series with the Department of Energy and leads the HPC Containers Advisory Council. CJ has contributed to both hardware and software technologies for the past 20 years and has over 100 patents. He's a community builder with a passion for extending the core capabilities of hardware and software platform from HPC into AI, data science, and visualization. Before getting his Ph.D. at Carnegie Mellon University, CJ did stints at a couple of startups, worked on a voice recognizer and a supercomputer, and he's delighted to have worked on volume products that his mom used. With that note, welcome, CJ. You have the floor.
Thank you so much. It's great to join this great crowd and audience. So thanks in advance for spending some time together looking at some things. So I'd like to paint a vision of data centers. We see more and more happening in the cloud and more AI assistants to better enable people to do their life's work, whether that's in science or in other fields. Our observation is that there are going to be so many more data centers that are going to be needed, but it's really not just about taking sheet metal out of boxes. There's a tremendous complexity, probably several PhDs worth, involved in bringing it into operation and achieving reasonable SLAs. So given this explosion number of data centers, who's going to make that work? And those are all going to need performance, efficiency, security, and we seek to democratize that so that we can make it available for all, so that the very many enterprises that want to have their own version of this to stand it up on their own data centers can do that, and we can bring that sort of to bear in the world around us. So we've kind of used we have a notion of sort of dog fooding things. So we've created our own data centers on which we've run the MLPerf, and the MLPerf is something that we use to drive a lot of the other innovations and deployments that we have inside of NVIDIA. And being able to stand up and scale these systems quickly has been really important in setting records and doing lots of real good work there. So to this end, I'd like to look at some energy efficiency considerations. So first point I'd like to suggest is that accelerators are the key to moving the needle and reducing worldwide energy consumption. So to lots of folks, you could debate about, should everything be happening in the cloud? Does everybody need to have everything accelerated by AI? I think those are, as Gadi said, those are some unsolved questions, right? But if that's going to happen, and to the extent to which that's going to happen, I think we really need to take the responsibility to be efficient in the way that we do that. If you're going to make an accelerator, you really need to have great APIs for that and a whole mature ecosystem, because it's not just about sort of doing a stunt and showing one great number, but really being able to solve an ever-increasing range of problems and going after the general programmability. And software tuning of that is going to be really important, because I haven't met too many people that make things perfect the first time. And so it takes a while of looking to see, hey, where can we improve things? So I'm going to talk about some of the analysis experience that we have and some of the tools we have that are helping us, first in research and some of the things we're deploying. And kind of a key theme throughout all this is looking at data center utilization, of scaling, of making it so that you can partition it when you want to work on small problems, that you have an automated way of applying best practices, and doing all that in the face of increasing security concerns. And we'll kind of wrap up with that. So first, I'd like to look at kind of the component, at the component level. What are you going to use as your building block for the data center? And in particular, long ago, everybody did that with CPUs. More and more people are recognizing we need some sort of accelerator in order to be far more energy efficient. This is kind of a no-brainer. So we tried to do some analysis in this space. We took some speed up estimates of MLPerf with AI, and some things that we had done in our own performance lab on HPC, and converted the energy efficiency by scaling to the TDP of the server. Then we compiled some of the other data from IDC and Hyperion on server shipments for AI and HPC workloads, and then took their estimates of 200 terawatt hours of energy being spent across, per year on all of these servers, and kind of computed the average energy, annual energy usage, and then tried to take that and essentially apply that in, so what happens if those were done with CPUs versus what happens when they're done with GPUs. We also have kind of a new thrust in the company that happened to drive DPUs, the data processing units, and looking at those, if your average one of those at the higher end is on the order of 75 watts versus something that's, a kilowatt or something for the rest of the server, can you offload that? And if you can offload a significant fraction of the work to that, that's more power efficient, then that can offer you a whole lot more benefits. So let's dig into some numbers. On the right-hand side, you'll see references for the MLPerf IDs for GPU and CPU results. I didn't show each of the performance numbers here, but you'll see the effect of those in a moment. So we took essentially trying to make a comparison between Intel CPUs and NVIDIA's GPUs. We took all the results that they had, what they published, and at the scale that they had published it at, and said, okay, what do we got that is the best match for that, so that we can make an apples to apples comparison. So that yielded 2 different results for training and 5 for inference. We also picked a half dozen different HPC apps. Now, anybody knows that what we're really trying to do is to solve real problems, real people's business, and that no benchmark is ever perfect for that, and that you have to come up with some way of weighting those different benchmarks. That's super subjective. So we just tried to say, what are the mins and maxes across what we had here, and what are the geo means, specifically when we look at the energy efficiency improvement in comparing NVIDIA and Intel. So what do we get when we do this? It's it's about a 20x speed up, just looking at the energy efficiency. So we take essentially the times that are quoted, and then multiply that by the power, and to get the, and multiply that out to get the watt hours. So that's a significant number. Then you can ask, okay, so if it's better, if it's more efficient, what kind of real impact would that have? You can see over time on the left that the sort of distribution of different kinds of servers really shifted from the traditional to things happening in the cloud and at hyperscale. And so we tried to look at what's the number of servers that are in use by workload for each of AI and HPC. And if you hadn't noticed, AI is a lot bigger than HPC. And this is because, if you're even a mom and pop hardware store and you're not using AI someplace, you're kind of getting left behind. So many people are trying to do this. So then if you take this and you multiply out, what's the difference that we just showed in the last slide, and applied at scale across the world for what it is that we have from IDC, Hyperion, etc., you end up with something like 11 terawatt hours. That's a crazy number. I'll just show briefly what you would do in the DPUs. There were some estimates by Amazon, AWS, that about 30% of the CPU cores are required for the hypervisor and operational management that could be offloaded to the DPU. So this hasn't happened yet. This is a projection. So this is based on some Korean estimates there. And if you look at what the TAM is for servers sold, and take about 25% of those as being acceleratable, and they're at 75 watts versus like the rest of the thing being a kilowatt, then you get about 7.7 terawatt hours. So just for fun, let's ask, what does that look like? What are the equivalents? That's like 1.7 million passenger cars driven, or 18 million barrels of oil, or 1.4 million homes of electricity, or you can look at this in coal-fired plants or acres of a forest. We tried to drive all these in terms of the CO2 efficiency for these things. And you can get similar kinds of numbers for the DPUs. Okay, so we know that that's not a perfect analysis. We made a bunch of assumptions. We essentially are looking at TDP instead of something that's actually measured. And we don't know exactly out of that 200 terawatt hours, how much of that is accurate. And we're sort of assuming that this is based on all AI and HPC workloads switching to GPUs, and that's probably not going to happen. But it gives you a sense of sort of what some of the opportunities are. And there are things that we would like to improve in this and sort of making more direct measurements. So let's move on and look at programmability. So again, you could essentially GPUs are ASICs, right? So there's special purpose machines that you could use that, and DPUs that are there for AI, and the DPUs are sort of ASICs, if you will, loosely speaking here, for that you could use in the networking space. So you can make a super specialized animal down there that can do all your work for you, but you have to talk to it. You have to actually do something with it, and you have to want to do lots of things with it. So from a developer standpoint, we just want to stay out of the way and let the developers do their life's work. And that means being able to let them express things at the semantic level, even in Python, without having to overly tune for each individual microarchitecture with all of its vagaries, etc. So I'm just going to take you on a little bit of a perspective here of looking at the end-to-end platform. So it seems that we have the fastest AI supercomputing system. But it's not just that we have one, it's that we're doing lots of those at scale. It's not just that we have a GPU, and not just that we have a DPU or the switches, or we have network, we have NVLink that can hook these things together. It's really about the whole stack of being able to have OSs and the libraries and CUDA-X and all these AI models that you can pick up and retrain or whatever for your particular applications, and then get those to work at scale. So for us, we really think this is about a full stack computing platform. So Kushal is the product manager for Magnum IO. That kind of sits at the bottom of this. You can think of it as multi-GPU, multi-node, and it's all the data movement, data access, data management for being able to do this. One of the directions I expect that to be extended is more and more use in AI. And all of the CUDA and all of the different vertical stacks are on top of this for a significant number of SDKs we have in this space. And lots of people using that. So it's really about the ecosystem of having a whole set of people who know how to use these technologies and who have well-tuned apps, and they're finding them in the spaces that they need them. So again, there's more. If you look at this layering from hardware technologies up to the application frameworks and the different kinds of work that we're doing in this space, it's important not only to have all this, but also to have certified and validated solutions where you can say, I know that if I download this container, I know where to go to get the latest and best performing container. And I can take that and know how to execute it on a validated platform and be able to roll from there. And this is done very much in partnership with lots of others. Okay, so let's talk about performance a little bit. So in the performance space, we essentially have several different layers of the code optimization, of the applications and algorithms, and the DC resources, and just making sure that things are healthy and ultimately improving the architectures. And all of these are multiplicative. So I'm going to look at some case studies. This is based on about 60 workloads or so that we looked at, the top guys by time, and where they were making inefficient use of resources. I'm just going to offer some highlights here. So we look at efficient nets. We said, hey, there are a lot of people that are running these with misconfigured jobs that are requesting the AGPUs when 4 are enough. They're sometimes using old containers that are not the most optimized version. So addressing those, 1.45x boost. We have these tensor cores that you can use where if you have lower precision, you can get more work done per unit time. We call that automated mixed precision, or AMP. And so when that's turned on, you can get a lot more. This is again with ResNet 152. We saw idle GPUs and people not using AMP. So we fixed that, and I bought 1,500 GPUs hours per week. We saw cases where people were bottlenecked on data loading because they hadn't, the user parameter to configure the number of data loaders there was set to 1 worker. And by switching that, we got about a 6x speed up. We had other cases where the standard configuration and ratio was leaving things starved because we needed actually more CPU cores or CPU memory for that particular work. And so that ended up having significant impact. And there are other cases where the batch size was too small. And so by making adjustments there, we saw some significant speed ups. So we also looked at a whole bunch of interactive jobs coming from Jupyter notebooks and kind of saw some significant opportunities for here. So I'll try to just summarize sort of who can do what by pulling out some of the main ideas for what we just looked at. In many cases, the users can do something. They're user level parameters that they can avoid idle GPUs or tune the data load workers or make sure that they're selecting things for the right CPU to GPU ratio. There are other things. I'm expecting that most of this audience is users rather than developers, but developers have a place here too of using the lower precision via AMP and tuning the map size and making sure that you're using the newest libraries. So what are some things that we can do? These are some things that we tried. We tried looking at finding applications where, hey, if across a 16-hour period for at least 4 hours you were using less than 20%, maybe you were idle, I'm going to kick you off. And then let's go have a conversation. So we found that by implementing some of these policies, we could save about 2% of our capacity in the Nvidia GPU cloud. We went and looked at detecting automatically idle GPUs. 9 out of 10 cases, we found that those jobs, were intentional because they needed more CPU cores or more CPU memory. So this suggests that there may be opportunities for heterogeneity of when you need that, detect that you need that, put those on the right places that have, the appropriate ratio. We created a bunch of tuning guides. And then we essentially tried something now that's kind of a research project that we have of automating the process of looking at a whole bunch of these different items that are listed below, from the libraries to, oops, I left debugging on, didn't want to do that, or I didn't enable some feature like AMP, or I could have done more to fuse operations so that I could be more efficient. And trying to make recommendations that are like, hey, did you realize this is going on? So we did 2 things. So the first stage, we essentially had some experts that manually applied what it is we found from that tool. So we had the semi-automated analysis, and then they did that. And you see across these different applications, we got some pretty significant speed ups, sometimes 2x, sometimes maybe 4 or even 8. And many of those were done in just a few hours. So if you think about how many times people are going to run these applications over and over again, and we get this much benefit by a couple hours worth of work apiece, that's pretty significant. So driving up the GPU utilization and applying a bunch of different optimizations. Here's something else that, and I'm just really excited about. So imagine a world in which you could essentially watch something run based on historical jobs and maybe even in the future in what's queued up, and essentially look at, so what happened, right? What did I learn from a tool like this, and how could I have done things better? And how could you rerun things to be more efficient and effective? So run things on a canary and then monitor it, and then take these GPU workload environment and evaluation and pass a bunch of information back, and then essentially rerun it. Well, what if I'd run it that way, and eventually be able to say, hey, based on past experience, you should run it this way automatically. And if you can opt into a system that'll just run it better and smarter. Okay, so kind of pie in the sky, right? Could you really do that? Is there really any good that you're going to get out of that? So we tried that across several different workloads. And we got some noticeable speedups. A lot of times you'd be happy with 1.1x. Sometimes you get 24x. That's pretty good if you can do that. And that's basically fully automated without anybody doing any optimization, just essentially well, you did manual improvements, but you didn't do, it figured out for you. There was no expert that went and figured out what your problems were. So kind of the direction we'd love to go in here is to be able to automate the application of these learnings as well. So that's yet another future. So these are experimental tools that we have working in my organization. We have some that are public. Our tools guys have something called a DL Prof viewer. That's obviously way too small to see. Let's zoom in a little bit. So you can look at a chart of your GPU utilization, of where your GPU ops are being spent, like how much of it is in the tensor cores, how much is eligible for the tensor cores but didn't actually get in there, and other ops. The time that you're spending in the kernels that are using the tensor cores and memory kernels and other kinds of kernels, so that you can see this. By here, I don't mean OS kernel. It's just like what kind of a kernel are we talking about? And then the tensor core kernel efficiency chart. So that was for the tensor core. There's a middle row here where you can look at the overall performance summary, how you doing, and give you kind of a summary for over time, how are things going for each of the iterations taking, and what are some of the top 10 GPU ops, so that you can kind of look and say, hey, I'm using nickel, or whatever else that I'm using under here, so that you can see what some of the dominant effects are. And finally, you can look at the system config and get some expert systems recommendations as to what are the kinds of things you can do, and more of a panel here that gives you some guidance. So this is all in service of, yes, you can go and you can take something. There's an amazing team of heroes that are going to go and do ML perf, but how about the rest of us? How about actually making that so that it's easier for the developers to use, for folks that are helping with the tuning recommendations, and ultimately making it so that the end users get some feedback and maybe even can opt into some automation. Let's see where that goes as we move forward. All right, next topic here, I wanted to kind of look at the efficiency of the data center and its utilization overall. Let's start with scaling. So suppose I got this basic box, and a little blue thing here is a CPU. And in that, I'm going to put some threads. If I got a bunch of threads, maybe I don't want a CPU anymore. Maybe I want an accelerator like a GPU. And now, if I really want to be as efficient as possible, anybody who's looked really at power, you know that it's wires and it's going over the network, that if you have to move data across the chip, it's not so bad. Between chips inside a given box, you know, it's not so bad. But if you have to start sending things a long distance away, then that starts to cost you. So by packing more densely into the same platform, you can do better with this. And the interesting thing too is that it lets you kind of, those IB, the InfiniBand connections are kind of sharp edges, and we can sort of push those out by attaching as many of the computational resources as we can with a memory bus link as opposed to a network link. We call this NVLink. And across that, you can just do a direct load and store. And think about it, direct load and store is a whole lot more efficient than calling through a bunch of MPI code and going through a runtime to get there. I'll just give me my data, please. Thank you very much. So now if you do this at a scaled platform, it's even more important. And so next we're going to look at some data in this. But when you start to think of this scale, at every single level, you want to ask, how can I do things most efficiently with adequate generality and programmability at each level, with what I do inside the GPUs, with the interaction between the CPU and the GPUs among themselves, And this is kind of, again, where this Magnum IO thing comes in, at the multi-GPU, multi-node thing. And if I'm going to start communicating across these at scale, one of the things that I care a lot about in the AI space is all reduces. Because at the end of every, whether you're doing forward or backward, at the end of each stage, you're basically doing an all reduce and communicating with lots of other folks. So I could, in a large network, I could go all the data to everybody else where they could compute it in somebody else's computing element and then send it all the way back. Or I could do that hierarchically by putting some of that smarts in the network and do that essentially in networks and switches that are optimized for bandwidth, not just for the HPC thing that some go after of trying to do things for latency. So that's, again, all part of the stuff that we're doing with Magnum IO. Okay, nice theory, doesn't matter. So let's look at this. Data is a little bit dated, but it's still relevant. But we did an experiment that looked at essentially 20 CPUs and versus just doing it with a rack. And of 20 CPUs and 800 was back in the Pascal generation P100s at 32 kilowatts. Or we had 7 racks to get the equivalent performance on VASP. We needed 7 racks at about 8x the power. If we did this with Café, then we needed 9 racks and 11x the power. And so if you look at sort of the ratio of the non-compute stuff, the compute servers versus the non-compute stuff in the two cases, it's radically different. So spend all your power on getting useful things done, not on shipping things around, data around, and managing your data center. So now we kind of looked at efficiency when you integrate things. So great, there's a big move to make huge chips, to have lots and lots of stuff going on these transistors that are happening. So now how do you start to scale that? Well, we have something inside. We're making these GPUs so big that a lot of times people don't even need that much power. They need that much computing power in aggregate, but not for individually. And as we can see, sort of the vast majority of computing time is going to be spent on training, on inference, or at least the fraction of the cases are going to be in inference rather than training. There are arguments that with NLP, training is going to get really big, and there are cool things going on there for natural language processing, but we'll see how that balances out. So what could we do? We could essentially, each of these things could be a slice inside the GPU, could slice them up into smaller partitions. And then depending on what it is you want to do, you can have variable size partitions that we use for this. And we call these multi-instance GPUs. And this can significantly improve the effectiveness and the energy efficiency inside the data center. So what else can you do? So other things you can do is to basically size the workload to the electrical workload. So if you have a massive system, but you're not using very much of it, then you're wasting a huge amount on your cooling infrastructure and on idle power. And there are different numbers in the industry out there. Some people say a quarter, a third, or more being spent on idle power. So you kind of really don't want to waste things not doing anything. So you could say that you can look at peak in terms of peak flops, but what really matters is getting the work done and evaluating how effectively you can make use of the computing resources. So you can think then in terms of the effective peak. And across all your workloads, if you got them to get to 80% of what some crazy ninjas did for ML-perf, that'd be great. And you find that the effective peak itself is much better with GPUs. So in order to achieve this, you want to make sure that the application has been well tuned. So you can use highly tuned containers that you can get from a well-known repository that not only is kept up to date with the best performance, but that also has scrubbed for CVEs and that is sort of being maintained and tested so that you can have confidence it's going to work. We offer one of those in NGC. The other thing is you want to look at the PUEs, the power utilization effectiveness, and kind of the standard is to kind of keep that cooling and compute to compute ratio under 1.3. So want to continually evaluate this and find the need, how much improvement is needed, and figure out the means for improvement. And so we saw that back in the analysis we did for a number of those workloads, and continually to drive forward the infrastructural inefficiency. So we have lots of cases where we're doing considerably better than our 1.3 here. So what are some directions that you could go in automation in this space? So one is that you could take the user parameter settings that people are, that's not a developer problem, that's whatever the user is doing, and look at them and evaluate how effective they were and give the user feedback, or to automate that. Again, these are things or directions that we'd love to move towards. Another is to characterize each workload, to maybe group workloads and say, oh, this workload is more similar to these things. And if you take, for example, different workloads of a common type, and you put them on a similar subset of resources, it actually makes it easier for you to do the analysis at that granularity of like this portion of your network that's running this type of workloads than if you had 6 different, completely different types of workloads running on every other box or CPU even. That'd be crazy. So, but there's, if we can essentially do the analysis for the performance relative to the effective peak, look at the GPU, look at the tensor cores, look at the IO, and characterize those to see where should we be spending our time. And then you could also look at, so you may in a data center have a variety of different generations of equipment. This is not uncommon. So different workloads may benefit more or be hurt more by running on an older generation or versus a newer generation. So how do you affinitize those appropriately? Starting to take a look at if you're doing an all reduce and your particular job takes up 10% of the data center, but you're kind of splayed across the whole data center, that's going to be pretty inefficient. So you want things to have good locality so that even in your switches, especially if the switches are essentially doing reductions for you, that those are localized as much as possible. And that only saves you in terms of the time, because if you had to make more hops to go all the way up to the spine and back, that would hurt you in time. But also the end, by having better grouping, you can make better use of the acceleration in the switches. But it's also the energy, because the fewer hops you make, the less energy used in this space. And so those are some things that we're looking at. Now, finally, I'd like to talk a little bit about shareability. So there are a number of resources that you could consider sharing. You could have long-in nodes, you could have a single Slurm instance, or you could use something like we have something called the base command platform, or a top. You might have a top of rack or your storage or your other control nodes, and you could make it to say, I'm so worried that somebody's going to get at my code, my data, or interfere with me, that I, as an institution, have to have all of my own resources. I'm going to pre-buy all the resources that I need, and hopefully that's enough. Otherwise, I'm going to be overly constrained. And hopefully, I need exactly that amount over time, and I'm not underutilizing, which could kill me with respect to efficiency. There's a better way, shareability. But the concern is, with all these really precious models, right, as people would want to break in and get a model, or it's the time of being able to do this. If I have a recommender system and somebody interferes with it and I can't get a recommendation, I lose a sale. So there, across all of these different kinds of things, we see a lot of concerns about that. So now we want to drive towards a system that has zero trust. So we want to isolate, use isolation to reduce the need for trusting other users or the integrity of the whole infrastructure. So this zero trust, the key principle is to have least privilege between easily managed users and components. So compute nodes, they're the ones that run the containers. Somebody could break out of their container and root the compute node. Do we really want them to be able to tap into the rest of the management infrastructure and get to everything else in the user storage and network and storage? There's a little thing there, like you can't stop people from yelling out their username and password while they run down the street, but you do want to make it so that you can contain the damage that they can do to anybody that's sort of on that given compute node and nothing else. So how is it that we do this? So our kind of scaled systems at the moment that we make, where we have a recommended system for the storage and network and computing and put all those together, is called the superpod. And so you might, it used to be just the pocket protector guys that were using this big iron, and now it's lots of different folks that are using it. But now if they're trying to share these, you may have a job, these were all color coded, they're all running to run the same time in the same system. So who is it that's going to create tenants and allocate nodes and configure things for isolation and configure the DPU and launch the job and clean up? That's something we have that we're come out with now called the base command manager. And this is basically our way of doing cloud native. So it does the provisioning, configuring, managing, securing, and the tenant job management. And we have a number of these things that are already supported. And we had some great work that I've been driving lately for prototyping additional features that essentially bring security and isolation in all of these different areas. And so what's the principle here? When you go into a bank, you don't expect to be able to touch the money drawer. You talk through a little window, and basically you're an untrusted agent making this request. And if all goes well, they shove lots of green or whatever your other favorite money color is through the window. So the principle here is that we want to use a restricted interface for the control path, but have an uninhibited data path that can operate at full bandwidth. And so what we do is that for these untrusted hosts, we introduce a new element, the DPU, which we referred to earlier as a potential source of some power savings and cost savings, that is on the doorstep, that's reachable from the PCI, and the control path stuff of the establishment of connections goes through that, but the data path runs straight through this trusted infrastructure. And so that you can use the techniques like these essentially to avoid distributed denial of service attacks, for example, or you basically make it so that you don't have to trust the host to come up with all the information it needs to be able to make protected accesses. So we're trying to use security as kind of the foundation of a superpod, securing the compute and the storage and the network. And we have a variety of different services that we're putting on the DPU to essentially manage and attest and do the mounting and give us various different forms of isolation in the space. So I just want to end with a call to action. First, use accelerated computing. When you use accelerated computing, make sure that you're using the fundamental components for this larger system that are power efficient, that are scalable, that are partitionable for even lots and lots of small jobs. Those are going to be really important for inference and for programmable accelerators. Make sure you're using the best software. Get the latest containers, for example, from the Nvidia GPU cloud. And make sure that you're managing efficiency at the whole data center level, because even if you have something that's running really well inside of your smallest component, you can waste a lot of energy by underutilizing things and having an inefficient system. So software and people and administration matter a whole lot there. Work with users on their efficiency so that they're putting their best foot forward and they're not shooting themselves in the foot by leaving debugging on, for example, and give better tools to guide the users as to how they can improve things and to automate the affinity, for example, on heterogeneous resources and for the sake of communication. And being able to share those larger infrastructures allows many different parties to enjoy the benefits of the economy of scale by all being able to work together and share a common system while not having to being forced to trust each other so much because of the isolation that's been put in place. think I'd like to rest there so we can see if we have some time for questions.
Perfect timing. I was about to do a time check. Thank you, CJ. So if there are any other questions, please raise your hand. While we're waiting, I have a few questions. Somebody else has a question? Okay. So something that it's been shown on your talk is that there is the belief for a holistic ecosystem to address AI. And there is these prior talks talk about that AI as is going and the trend that is going, it might change. And so the workloads that we are seeing right now might be different in the future. So how is this holistic ecosystem is going to be addressing that? Or what are the predictions that you have on the workloads that are coming?
Questions. So we, the way that we try to approach this is to wait to be reactive, but essentially to try to anticipate where the major areas are for development. So if you look at work that we're doing in natural language processing and so on, we're driving a lot of the work that's in that space and joining many others that are doing it. We build our own systems and try to tune them in anticipation. So we try to be sort of a leading rather than lagging indicator in that space. A second component to the question is the question of how do you prepare yourself, right? So yes, you can keep looking at new verticals, new different kinds of applications, but the key thing that you want to do is to make sure that you have a well-architected system that's modular and that's built from the ground up. So Kushal and I are working together in Magnum IO. So at the lowest level, we're always looking at driving forward the underlying technologies and building up sort of the lower level software components that can use those, both for different programming models, and then on top of those, libraries are built. We're doing more at the edge, for example, and in the edge space, we're essentially saying, hey, a lot of things you do in the edge want to have visual processing involved. You have an instrument, you're looking at taking those observations, and you want to get the human out of the loop so that you can make very fast decisions and get feedback to drive the experiment that you're doing. And a lot of that operates in the visual domain, which is a very efficient way to represent data, and allows you then to be able to take all of the work that we've done. We're also a graphics company in addition to a data center, tons of different libraries that we're then trying to take and knit together and look at how we can work those into whole pipelines. The stuff we're doing in Clara for healthcare is an example of this. So we expect the rate of new innovation, of new applications is just going to get faster and faster. And if you don't have all of those building blocks in place and lots of practice with being able to figure out how to fit them together and compose them into larger and larger systems and practice doing that yourself, it's going to be hard to keep up.
I see. But in terms of predictions, what are your predictions for the workloads of AI that could come in the future and how that aligns to the heterogeneity of the backend? So something that you mentioned is there is a trend to have heterogeneous backend. So how is that going to be aligned? What are your predictions on that? So
lots of predictions that could be made. My expectation is that, you know, this is something that you already start to see. I don't know how many of us have had some time in the last week when we were on hold or had to talk to somebody and they got the information wrong, or we had to give the same information 3 times when we called into some call center. It can get frustrating, right? So having, it's actually possible for a machine who sounds remarkably like a human to be much more accurate, much faster, and much more effective at being able to do the natural language processing to get it right, to make sure that we've got it right, and to be able to drive that forward. I think that there are ways that we're used to doing that when we, you know, pick up the phone and call something, but I expect that much more around us, many of these kinds of things that we used to, you know, my kids are going to say, you know, what's that remote thing, right, that you have, right? Why would you need a remote for anything anymore? So there are a lot of the different things that we're used to using with much more automation and autonomy, whether they're vehicles or systems or things in our homes or whatever, expecting a lot more of those things to be driven by AI. And some of the things are going to work locally and have all the compute they need, but there's also going to be much more of a continuum, a spectrum between what's done at the edge and what gets done back in the cloud in a server. And figuring out what information to pass up back and forth, where there are opportunities to bring specialization down to a base tower, for example, as opposed to in the cloud. There are a lot more of those kinds of trade-offs that need to be made. And at every step of the way, I think a lot more of that's going to be driven by AI.
Thank you. Is there any other questions from the audience?
No question, just a comment. Thank you, CJ, for presenting. This is great. Just another note to the rest of the folks is we are hiring in terms of, lots of opportunities for interns, developers, as well as engineering managers. So please reach out to CJ or me to if you want to join this wonderful journey. Thank you.
Love to hear from you. We just want to help people do their life's work, and that's really exciting to be part of. So,
thank you.